Okay, so what we'll do today is continue the discussion on synchronization. I will talk about deadlocks, okay, a new topic, and I will spend the last 20-25 minutes doing an exam review, see if you have particular questions about the exam and so on. Okay. All right, so shut your laptops, devices, etc. Okay, so just quick recap. We've been talking about synchronization. Last time I talked about two specific problems, the reader-writer problem, where you allow multiple readers concurrently to access a shared object, but you ensure mutual exclusion for writers. Okay, and then you can do this using this notion of a read-write lock. We saw how to implement read-write locks for maximizing concurrency for readers. And said if you really have to use read-write locks in your code, you don't actually have to use the code we showed because Java supports read-write locks out of the box, and so do pthreads. Okay, then we looked at this other problem called dining philosopher problems, where you have multiple processes or threads that are contending for shared resources. Okay, and we looked at how you can ensure that every thread or job is able to make progress, is not deadlocked, and so on. Okay, so that sets the stage for this discussion on deadlocks that we are going to go through today. And as I said, towards the end of the class, I'm going to talk about exam 1 and all the material we have covered so far. But before we end the discussion on reader-writer, producer, consumers, dining philosophers, when we talked about all of these problems in the abstract, okay, but what you need to take away is that these problems occur over and over again in real-world applications. Okay, this is not some abstract toy problem that we studied just to see how to use locks or semaphores. They are characteristic of real-world applications and their needs. And here are just a few examples of where these problems actually arise in practice. Okay, so our producer-consumer problem. If you have an audio or video player, you have a client, let's say it's in your browser, or it could be a separate client, you're playing, let's say, video from YouTube or Netflix or whatever. The player actually uses producer-consumer, where you may have a network thread that is accepting data that's coming to you streaming over a network, okay? And it puts this into a shared buffer. Okay? And then there are other threads that pull data out of this buffer, render it, and display it on your screen. Okay, so the shared buffer allows you to sort of implement a variant or version of producer-consumer problem. I already mentioned the web server example when we talked about producer-consumers. Here you may have web server, it could be the Apache web server or any other multi-threaded web server. Typically you have what is called a master thread and slave threads. The master thread is responsible for accepting HTTP requests that come over a network socket, sticks it into a shared queue, that's your producer-consumer queue, and the slave threads are essentially the consumers. They pull requests off the queue and process them. These are user requests that have come. So this is how many web servers are architected. Okay. Now readers and writers, there are many examples. They frequently arise in databases. If you have any database applications where there are lots of entities reading data from your database and some entities writing data, you have readers and writers. To maximize database concurrency, rather than using a straightforward lock, right, which will lock out other readers and reduce concurrency, typically databases use read-write locks, where read queries, okay, queries that only read, are allowed to have parallelism. Okay, think of online retailer where you may be searching for a book. Okay, you send in a search query for a book, it just looks up the database and returns all matching results. Okay? Other users may be conducting searches at the same time. There is no reason for all these searches to be sequential. Okay? You can let them access the database in parallel. They are not modifying data, they're simply reading. Okay? On the other hand, if you want to update your catalog, okay, of books in this store, and you have a writer, in that case you actually lock the database or make whatever updates you need to make and then release those locks. Okay? Same is true in banking. Okay? That's also your account information is stored in databases. You may have read queries on your bank databases. Let's say you go to an ATM or a teller and ask for your bank balance, or you log into your online banking system and look for your bank balance. Those are all readers. Okay, and if you're making deposits, your jobs that are computing the interest, if your bank is paying any interest at all. Okay, so those are all write transactions. Okay, those will require write blocks. Okay, so again, very common scenario of having readers and writers and distinguishing them in order to maximize concurrency for users. Okay, dining philosophers is another common problem that occurs. Okay, simplest way to think about it is let's say you're doing a hotel travel reservation that requires a lock on the hotel database, airline database, car rental database. Each of them may be separate databases, and you need multiple locks in order to proceed. Okay, and that's an example of dining philosophers because multiple users may also be trying to make travel reservations. Okay, so whenever you have entities that need multiple locks in order to achieve their goal, you have a variant or an example of dining philosopher. Okay? Just to give you some flavor of real world applications where these problems arise. Okay? So what you have are abstract scenarios, but when you have these example applications, you will have to implement some notion of producer, consumer, reader, writer, or dining philosophers. Okay. So with that, we will switch gears and start talking about deadlocks. Okay? We looked at deadlocks a little bit already in the context of dining philosophers. I'm going to formally define what is a deadlock. We'll look at conditions that cause deadlocks, okay? And then we'll see how you can avoid deadlocks or prevent them. Okay, so we will not go through probably all of the last bullet, but the first three we will finish today. Okay, so what is a deadlock? Okay, deadlock is a condition when two or more threads, okay, are waiting for some event to occur, and that event can also be generated by the same group of threads. That's an abstract, slightly abstract definition. Okay, essentially, it's a scenario where, or the common case where deadlocks occurs is when some threads hold locks or on some resources, and other threads end up waiting for locks, and nobody is able to make progress. Okay. Here's a simple example of two processes, okay, that are trying to grab a semaphore or a lock, okay, on two resources, a printer and a disk. Okay. The first process gets a lock on the printer first and then the disk. The second process gets a lock on the disk and then the printer. Okay. Opposite order. So what could potentially happen is process A can run and get the lock on the printer, okay, and then let's say context switch occurs and process B runs, gets a lock on the disk. And now A holds the lock on the printer, B holds the lock on the disk. Now if process A runs again, it tries to grab a lock on the disk. B already holds the lock, so it will wait. And then B will run. Okay, it will try to grab a lock on the printer, which A holds. Okay, so it will block. Now each process is waiting for the other to give up a lock in order to make progress. And neither is going to make progress. They're stuck. Okay, they'll wait forever. That's a very simple example of a code that is going to result in a deadlock. Right? In this case, the event that the threads are waiting for is acquiring a lock. Okay, that was a somewhat more general definition, but to make it more specific, each process or thread here is waiting for a lock. That's the event. Okay? And releasing of the lock is an event that the same group of threads can perform. But since every thread is waiting, nobody can make progress. Okay, so you're stuck in the middle. The processes are stuck. Is that clear? Simple example. Okay. So some terminology. First of all, deadlocks can occur when threads, processes compete for a finite number of resources, okay, at the same time. Okay, that's a common scenario when deadlocks can occur. And we'll distinguish between deadlock prevention, okay, which is algorithms that check for requests for locks or other resources and try to prevent deadlock, okay, if you see that there is a possibility of a deadlock. Okay. So you can have algorithms that are going to check whenever you make a request for a lock, saying, could this potentially lead for a deadlock? If so, you will actually deny that request, saying that's going to be a problem, so you will not let that request go through. Okay? That's deadlock prevention. You're trying to prevent deadlocks from happening in the first place. What deadlock detection does is it tries to detect deadlocks after the fact, after they've occurred, and try to recover from them. Okay? So in this case, you do not put any restrictions. You just let the threads run. Okay? And then you check every once in a while, has a deadlock occurred? So for instance, in this case, if you're doing the latter, you will let the processes run, and if they actually end up in a deadlock, you will try to detect that condition and recover from them. Okay, two different techniques. One prevents it from happening. Okay? The other says let deadlocks occur and we'll try to deal with them after the fact. Okay? So you can have either of those two approaches in your system. Okay? Now, one thing we should remember is the difference between starvation and deadlock. Okay? They are not the same thing. Okay? We have seen starvation when we did CPU scheduling, if you remember. Okay? We said for shortest job first, you can have short jobs starving out long jobs. Okay, starvation is essentially a condition where a thread may wait indefinitely, okay? But there are other threads in the system that are making progress. Okay, so whenever you have starvation, some threads may be waiting, but others are making progress. When you have deadlocks, no one is making progress. Everyone is waiting. Okay, so that's really the difference. If you have a condition where some threads end up waiting but others are making progress, that's not a deadlock. Okay, that's just basically saying some threads are starving out other threads. But if everyone blocks, nobody can make progress, then we say we have a deadlock. Okay, so this is very important to keep in mind, that they are not the same thing. So techniques to handle deadlocks do nothing for starvation. Okay, is there any questions about this concept of a deadlock? Okay, so let me present 4 necessary conditions for a deadlock. Okay, what does a necessary condition mean? It means if a deadlock has occurred in the system, all of these things are true in that system. Okay, that's what's meant by necessary condition. Okay, so these are 4 conditions that are necessary for a deadlock, namely there's mutual exclusion in the system, there's hold and wait, and there's no preemption, or preemption is not allowed, and circular wait has occurred. Okay? What mutual exclusion says is that there is at least one thread that's holding a resource in a non-shareable mode. That means there is locks in the system or semaphores, and so there is mutual exclusion going on. Some threads are holding locks, okay, or semaphores. Okay. You have to have hold and wait. Okay. This essentially says that some threads are holding some locks or resources and waiting for others. Okay, so in this condition code here, you had hold and wait, where process A was holding the printer lock and waiting for the disk lock. Process B was holding the disk lock and waiting for the printer lock. Okay, so you need hold and wait. Okay. Okay, the third necessary condition is there is preemption is not allowed. Okay, which means that if you are holding a lock, it cannot be forcibly taken away from you. If you could, then you could trivially avoid deadlocks by forcibly taking away locks from processes that hold them and giving them to other processes or threads, allowing them to make progress. Okay? So you are assuming a non-preemptive system. No, we don't mean a non-preemptive CPU scheduler. We just mean that resources that you hold cannot be forcibly taken away. A lock cannot be forcibly taken away. You have to explicitly do lock release. Okay? So a thread can release a resource voluntarily. The system will not forcibly take away the resource from it. Okay? This non-preemption has nothing to do with non-preemptive CPU schedulers. Okay? You can still have a non-preemptive or preemptive CPU scheduler that's independent of it. This is just talking about resources that you hold. Okay? Once you grab a lock, you have to release it. Nobody is going to take it away from you. Okay? And the last condition, which is really the key one for our discussion here, is that there is a circular wait. There's a set of threads. Okay? There's a set of n threads where each thread is waiting for a resource that's held by another. So if you could actually detect a cycle, okay, you have deadlock. Okay, so thread A waits on thread B, B waits on C, C waits on A. Okay, now each is waiting on the other and nobody can make progress. Okay, so circular wait is an important, okay, perhaps of the 4, this is the one we are going to focus on the most at the moment. Okay, so in this example, very trivial example, you should see a circular wait. Clearly, A is waiting for B, B is waiting for A. That's circle. Okay, I mean cycle rather. Okay, so that's a cycle, and that's indicative of a deadlock. Okay. Now, what I just said can be sort of abstracted out using this notion of a resource allocation graph. Okay, your system or the operating system could detect whether there is a cycle Okay? By simply tracking which processes or which threads hold what resources and seeing if there is a cycle. Okay? Very simply put, the graph that you could maintain, the OS could maintain, may it look like this, where you have circles representing threads, okay? Square boxes representing resources or locks. It doesn't matter what the lock is. We just represent any lock you have with a resource. The square box and circles are threads. And we have two kinds of edges. This is a directed graph. Okay? You have edges that go from threads to resources and edges that go from resources to a thread. Okay? Now, if there is an arrow or an edge pointing from a thread to a resource, that arrow indicates, that is this kind of arrow. That arrow indicates that that thread has requested that resource. Doesn't have it yet, it has requested it. Okay? Edge in the other direction from a resource going to a thread, okay, indicate that that resource is held by that thread. Okay? So in this case, T2 is requesting resource R1. It could be printer, disk, log, doesn't matter. But R1 is currently allocated to T3. T3 is requesting resource R2, but R2 is held by T4. T4 is requesting R3, but R3 is held by T2. Okay, now you see that there is a cycle here. So this is essentially a cycle. Okay, so if there is there's a deadlock in the system, you will see a condition like this, that there is a cycle in the graph. Okay, is that clear? What a resource allocation graph is? Okay, so basically the claim we are going to make is because a cycle is a necessary condition. If the graph has no cycles, then there is no deadlock. Okay? But if there is a cycle, a deadlock might exist. Doesn't mean it exists, but it might exist. Okay? Because it's a necessary but not a sufficient condition. Okay, let me explain this because it's important to understand what this means. Okay, the other point I forgot to mention is these edges are called request edges and assignment edges. In assignment, it says that as the name suggests, that the resource is assigned to that thread. A request edge says that the thread has requested that resource. Okay, so there are request and assignment edges. But now let's come to this concept here. Okay, if there are no cycles, then there are no deadlocks. Okay? So what that also means is the OS can simply continue looking at this graph and run what's called a cycle detection algorithm. Okay, if you have taken 311, which I presume some of you have, you must have learned about how to write a cycle detection algorithm efficiently. Okay, this is one scenario where you would use such an algorithm. You just maintain this graph. Every once in a while, you go and check, is there a cycle in the graph? Okay? If there are no cycles, then you're guaranteed that there is no deadlock. Okay? Because if there's a deadlock has occurred, then there should have been a cycle. Okay? So if there are no cycles, you know that there are no deadlocks. Okay, but if there is a cycle, a deadlock might exist. It's not sort of indicated that it does, but it might. Okay, so just to rephrase that, okay, because we said that these are 4 necessary conditions. Okay, that means whenever a deadlock occurs, then all of this is true, which is also means that there is a cycle. Okay? So a deadlock implies a cycle. Okay? Now you should know that by elementary logic. Okay? So if you just flip that, okay, if A implies B, that says not B implies not A. Okay, you should know that, right? 230. Right? So because this is a necessary condition, basically not having a cycle implies that there is no deadlock. So all you need to do is run a cycle detector, and if there are no deadlocks, or rather no cycles, you are guaranteed that there is no deadlock. Okay? Now that part should be clear. So you can check, and if there are no deadlocks, there is nothing to do. I mean, rather no cycle, there are nothing to do. Now let's take the case where you do find a cycle. Okay, so what does this mean? Okay, this means that a deadlock might exist, but it need not exist. Okay, why is that? Before I say why, yes.
This example with just the A and B threads that were cycle. If A deletes it from B needs before B needs it, I guess. If you're both waiting on it.
Let me put up the code.
Yeah, so you wait for the printer, and then if you release it before you're waiting for this, then there could be a cycle during context switch, but they were released before he gets it.
So we are assuming that there is no, so this is the code, right? So releasing of the printer is occurring here in this code. Okay, so you ask for the printer, you ask for the disk, you copy a file, presumably you're sending a job from the disk to the printer here. Okay? And then you release the printer, you release the disk. So if you are actually holding the printer and you're asking for the disk, you're not going to release this because you haven't gone past the statement in this code. Okay, so the scenario you mentioned is not that code. That's a different scenario. You can write your code differently. Any other thoughts here as to why? Okay, so claim is if you find a cycle, okay, that may indicate a deadlock, but it's not a guarantee. Yes.
I guess the dining philosophers problem, it's possible that could run correctly, right? So that maybe the philosopher picks up 2 forks and it runs and it progresses and that keeps happening by chance.
Okay. So that's a good point. The point being made is, okay, this code is not always going to result in a deadlock. It may be that your scheduler actually runs process A, it grabs this lock, it sends the print job, it releases them, and then process B runs. Okay, so both locks are grabbed by A, you do whatever you need to do, then B runs, and if you alternate or the scheduler lets them alternate like this, there will not be a deadlock. Okay. So that is true. Okay, so there may be code that basically might run well a lot of the time, but every once in a while, if the condition we just said occurs, then you will have a deadlock. Okay, so this is not correct code, but it may run without any problems for long periods of time without even knowing that your code actually has a subtle bug. And that bug is only triggered in a certain when the threads are scheduled in a certain way. Okay, that still doesn't tell us why. So now, if you see a cycle, then in that code there is actually a deadlock. Okay, so that means you actually triggered the bad case, the bug has been triggered. Now let me actually explain what this means. So first of all, you should say that I only said this is a necessary condition. I didn't say it's a sufficient condition. If I said that this was a sufficient condition, that would have also meant the reverse implication. If it was both necessary and sufficient, then a deadlock implies a cycle and a cycle implies a deadlock. Because I said it's a necessary condition, deadlock implies a cycle. I did not say that it was sufficient. Okay, so you should basically say that you didn't tell us it was sufficient, so it should, which is why it may not occur. But let's try to understand why it's not a sufficient condition. Okay. The condition is not sufficient because you may have multiple instances of a resource, in which case you can still make progress in the presence of a cycle. And I'm going to show you an example where you will see a cycle, but we'll be able to actually make progress. Yeah, hence there will not be a deadlock. If there's only one instance of the resource, of each resource, then the cycle actually implies a deadlock and it also becomes a sufficient condition. But in the general case where there may be multiple printers, say, or multiple disks, okay, you may not have a cycle. Okay, in that code that I just showed you, you may actually have multiple printers, so you may be grabbing locks on 2 different, or it could be a counting semaphore, say. So in that case, you may not have a cycle. So coming back to just this very example, okay, here is the same example, but now you have 2 instances of resource R3. They are identical. So the thread, when it requests R3, it doesn't care which of the 2 it gets. Okay, therefore, for purposes of the application, they are identical. Okay. So now we do have, in this case, we do have a cycle. So you basically have the same cycle that you showed in the previous slide. Okay. Now let's take a scenario. So I'm now going to show, this is the case where you have a cycle, but we are going to be able to break that cycle. Okay. So we add a third instance rather than 2. Let's say now we have 3 instances of R3, and you have 1 instance of R3 allocated to a thread T1 that's not part of the cycle. Okay, so the same cycle exists. Okay, but now there's an instance of R3 that's not allocated to this to a thread in the cycle. So what would happen? T1 is not where T1 already has R3. It can make progress because it has the resource it needs. So let's say it does make progress. All these other threads are stuck. Okay, they are in a cycle. They are waiting on one another. They will not make progress. But this thread will make progress because it has not requested anything else. It is not waiting on anything else. It simply holds the request it needs. So at some point, let's say that thread finishes. Okay, it can take arbitrary amounts of time, but at some point that thread will finish. Okay, At that point, it will release that resource. Okay? Now, this resource is available. Okay? Simply because this resource is now available, it can be allocated to T4, which is requested it. Okay? T4 is waiting on R3. Okay, so now you can allocate this resource because these two resources are in use, they are allocated to these two threads. But once the third resource frees up, you can allocate it to T4. Now the cycle is broken. Okay? When you allocate that, this edge will flip. So it will turn from a request head to an assignment, and there is no longer a cycle in your graph. Okay? So there is no longer a cyclic wait, so all the processes will be able to finish in some order. So the reason the condition is not a sufficient one is because you may have multiple instances of a resource. Okay? And there may be resources that are allocated to independent threads that are not part of the cyclic wait. Those threads may be able to make progress. They will eventually release those resources. Those resources will be granted to some thread in that cyclic wait. Okay? And then there is no more a wait because that thread can start making progress, not blocked on any resource anymore. Okay, is that clear? If you had the previous scenario, this scenario, where there's one instance of each resource, this cycle is indicative of a deadlock. Okay, because there is no way you can actually break that cycle. There's no progress you can have any thread make because there's no other resource to grant. Okay, so in the special case where there's one instance of each resource and you detect a cycle, then it's necessary and sufficient. In the general case where there are multiple instances, we had a cycle here, but we did not have a deadlock because we could actually make progress. Okay, so that's the reason to keep in mind. So what that also means is if you blindly run your cycle detector on your resource allocation graph and find a cycle, that doesn't imply that there is a deadlock. You say there could be one. It may need more analysis, saying are these single instance resources, are they multi-instance resources? So without further analysis, you cannot tell. Right? But if there's one instance of a resource and you find a cycle, then you know that there is a deadlock. So there's no other way to make progress. Is that clear? Yes, question.
So, are the instances of the resources interchangeable?
Yes. So question is, are the instances of the resource interchangeable? When you say multiple instances, we assume that they're perfectly interchangeable resources. You say, I want resource X. Let's say I want a printer. I want to print on a printer. There is a bank of printers. Okay? You are assuming that when the application doesn't care which of the printers you print on, they are identical. So you can give any of those resources. Okay? Only in that case does this work. Okay? If you can distinguish between them and you want a specific type of that resource, that's no longer true. So if one of them is a black and white printer and a color printer and so I need to print in color, then you can't switch it with a black and white. That's not what the application is. So if your instances can be distinguished, then this doesn't make any sense. This is only in the case where the resources are identical, interchangeable. And then it doesn't matter which of those instances you grant. Okay? Any questions here? Okay, so we talked about, so now we will talk a little bit about how can you deal with deadlocks. Okay, so first we are going to do deadlock detection. This is after the fact. Okay? You will let the threads run. Okay? Every once in a while you are going to check. Is there a cycle? Okay? If there is a cycle, you have to do something about it because your threads may potentially be deadlocked. Okay? This is called deadlock detection and correction. Okay? So first, it basically is very straightforward. We'll essentially assume that the OS is maintaining a resource allocation graph. It's tracking all the locks, semaphores, threads, okay? And it's tracking what is allocated to what resource is allocated to what thread. So you will essentially run a cycle detector and you will try to break the cycle. Okay? So how do you break a cycle? I mean, there are only a couple of things you can do. You can terminate one of the thread. Saying there is a deadlock, they're all waiting on one another. No one can make progress, so we got to sacrifice a thread. Okay, just kill it. Once you kill it, then some edges in the graph will disappear because that thread is no longer in existence. Okay, your cycle is broken. Okay. Or you can preempt resources. You can say there is a deadlock, I got to take something away from a thread. Okay, so you allocated a resource, you can take it away. Okay. Yes.
Is non-preemption a condition for deadlock type?
Yes. So you said non-preemption is a condition. So if you couldn't do this, then you cannot use that technique. Okay, I was about to say that both of these are harsh measures. Okay? You do not expect that when you write some Java code and you do lock.acquire, suddenly the JVM is telling you after you granted the lock, there's an exception, the lock has been taken away. Okay? That's not what you expect. That's not the semantics of Java. Okay? Because Java doesn't assume that the locks are preemptible. Okay? So you never write code assuming that after you grab a lock in the critical section, you are given an exception saying, tough luck, there has been a deadlock, so you're taken it away. Okay? But that's the only way. You have to actually force changes in the system if you want to use this technique. Okay? You don't have to. Or you kill the thread. Okay? Suddenly your code is working fine, you don't see a bug, your thread just terminates. That's not an expected behavior either, because you will say the code seems right, there is no particular reason why the thread should have been terminated by the system. Okay? You do not expect either of those two things to happen. But if there is a deadlock, there is no other alternative. Okay? Reboot is the example of killing all the threads. If you cannot make progress, the system seems hung. Typically, you go and hit reboot. Reboot your system. You killed all the threads. Okay? That's an extreme case of a middle one saying you just kill all the threads, now the cycle is gone. Okay? So if you want to recover from a deadlock after it has occurred, you have to take some harsh measures, which is you will terminate threads or you will preempt resources, none of which are necessarily nice solutions from a programmer standpoint. Okay? But that's the only thing you can do. Okay? Now, there's some side points. First of all, cycle detectors are not cheap to run. If you remember anything from 3.11 at all, you will know that cycle detection is order n square operation where n is the number of vertices. Okay? So that's expensive. As the number of threads and resources grow, running an order n square algorithm takes time. Your CPU is just busy trying to detect cycle. The OS kernel is running, nothing useful is happening. So you don't want to run the cycle detectors frequently. Maybe you run it every 30 minutes. Saying if something bad happened in the past 30 minutes, you will wait until the next time you run deadlock detection, and then you will take some one of these measures. Because it's expensive. You can't run it at every context switch or something like that. That will mean running cycle detectors 100 times a second. That's far too expensive. It cannot be done. Okay. So those are harsh measures. Now typically, because these things are expensive or they require you to take extreme measures, OSs actually don't do this. This is why when you run the JVM, you could write code that will deadlock. The JVM is not going to do anything to resolve it. It could detect it, it could have done this, but the programmer doesn't expect that locks are taken away once they are granted and so on. Yeah, so in some sense, most operating system, runtime system, just leave it to the program. Say you figure it out. You can run cycle detectors, or you can just wait and say something bad happened and reboot or some such thing, because you are in control. You decide what needs to be done if your code doesn't make progress for some reason, or you feel that things are hung in your system. Many times system hangs may also be caused by deadlocks. Sometimes they're caused by running out of memory or some such thing, but many times it's just that there has been a deadlock, so some critical processes just stop working and the system as a whole hangs. Your common response is let's reboot, which is what the OS has said. You figure it out. The user has to decide. Okay, so that is deadlock detection and correction. Okay, so there are techniques, but they're expensive, and frequently the OSs will not implement them because the programmers or application designers don't expect certain semantics. Okay, so that is the reason they just leave it to the programmer. Other class of technique is deadlock prevention. Deadlock detection says let's try to figure out after the fact and try to fix the problem. Deadlock prevention says let us do something so that deadlocks never even occur in the first place. Is that clear? What is deadlock prevention? Deadlock prevention is saying we will actually ensure always that deadlocks will not ever occur by either doing something special. And we'll see what those special things are. Okay. So the simplest way to think about deadlock prevention is we have 4 necessary conditions for a deadlock. If one of those conditions is always false, then by definition deadlocks cannot occur. Okay? So if you enforce some restriction on your system such that one of those conditions is never true, okay, it's always going to be false, then your system can never enter a deadlock. Because if it entered a deadlock, it would imply that all four of those conditions are true. But we just said that we impose some restriction on the system such that at least one of those conditions is false. So that's a proof by counterexample or contradiction saying that's a contradiction. Okay, so what could you do? What restrictions could you pose? Okay, how do you convince yourself that if one of those conditions is false, deadlocks cannot occur? Okay, let's take the first one, mutual exclusion. Okay, we say that we want to make that condition false. Okay, what does that mean? Yes, question. Paul.
It's not mutual exclusive, then multiple threats can use the resources.
Okay, so no, not having mutual exclusion means that you will not explicitly not support any locks. You say that if you write code which has no locks, no semaphores, by definition there's no mutual exclusion in your system. And if there's no mutual exclusion, there's nothing to hold and wait or anything like that. So there will not be any deadlocks. Okay. Now that's not necessarily a good solution, because if you say now you write multi-threaded code and do synchronization, but there are no synchronization primitives. Right? So I mean, yes, you can prevent deadlocks by saying no locks allowed. Okay. Not necessarily a useful way to prevent deadlocks, but if you do that, then your system is guaranteed not to have any deadlocks. Okay. So that doesn't quite make sense to as a restriction. So let's say hold and wait. Okay, so hold and wait says basically you'll hold some resources and wait for some other resources. Okay, now this one you can actually enforce as a restriction. You'll say you will only allow code in the system that requests all of your resources at once and then releases them all at once. You will not say I'm going to request them one at a time. Okay. If you enforce that restriction in your system, then you're not going to have deadlock. Yes, question.
Do something like that where you have multiple resources you want, would you need a lock to be able to access the other resources, lock resources?
Yeah. So I think I haven't said how do you do this. This is just an idea, right? It says that we want to make that condition false. Yeah, how do you make the condition false? You cannot hold and then request something else. You either request everything at once, so either wait for everything or you hold everything. There is no such scenario where you hold some things and you wait for others. Yeah. So you say, oh, you atomically have a system that allows you to atomically grab all the locks you need at once. So either it's all or nothing. You either block for all of them or you have all of them. If you have that scenario, you will not have hold and wait anymore. Okay. Now that involves writing new synchronization primitives. We don't have any such primitive that says, is there a way for me to grab 10 locks all at once? Or block on all of them at once until all 10 are available. There is no such primitive we have defined. Okay. So you can enforce or not enforce, make that condition false by defining new primitives which we haven't yet sort of written. Okay, so that's not so. If you have multiple rocks on multiple resources, there is no way you will grab them all at once. You will have to write statements in lock1.acquire, lock2.acquire, lock3.acquire, and that essentially means you are grabbing them one at a time, and you could actually block. Okay, not a very good solution either. Okay. Third one says no preemption, so we are going to make that false and we'll allow preemption. So now if you detect a cycle, you forcibly take back locks and throw exceptions. Okay. That can be done. Okay. But as I already mentioned, when you write code, you don't expect that in the middle of a critical section, the lock has been taken away from you by the system because it fears a deadlock. That's not the semantics you are promised by a lock. You grab a lock, you have the lock until you release it. That was the semantics promised to. So either you change the semantics of a lock saying you can acquire a lock and until it is forcibly taken away or the code itself relinquishes it, you are guaranteed mutually exclusive access. You change the definition of a lock to mean that latter thing, then you can enforce this condition. But you cannot just take it away when the programmer is expecting that it belongs to the thread that's acquired. Okay? And there may be primitives that you can't just take away. It doesn't make sense to take away. If you're in the middle of a print job and you take away the printer, you printed half the job. Okay, that doesn't even make sense because you wasted resources there and you now give it to some other reason. job. Okay, so in some cases this doesn't even make sense, and in other cases you make programmers very unhappy. Right? So the only thing you can really do is the last one. You will ensure that circular weight is not going to happen. Okay, so you can always write code which will guarantee, if you write it well, that there will not be any circular weight in the system. And yet you will be able to accomplish your task. Okay, so if you go to the very first example, okay, the way to avoid circular weight here, okay, is to simply flip these two statements. Okay, each thread first acquires a lock on the printer and then the disk. Okay, then you just taken out circular weight. Because if process A has already grabbed a lock on the printer and process B, first thing it does is grab a lock on the printer, it will block there immediately. It's not going to actually, and then, yes, your question.
In this scenario, you need every thread to block every resource you need.
You will still allow every thread to grab independent locks on every resource you need. All we have done is we have enforced an ordering on locks. Okay, that's your question.
What if process A can get a lock on printer and disk before context switches? Would there still be a
Yeah, so if you actually always, if process A and process B have the exact same code, which is this code, here we flipped it, so if you flip it back, the code becomes identical, then no matter what happens, you are not going to get a deadlock. Okay? Process B may block while process A holds the lock, but that's not a deadlock. It's simply waiting for the locks to become available. Okay? So you can grab a lock on the printer, you can grab a lock on the disk, fine, context switch to some other process. Maybe you context switch to B. B will block on the very first statement, which is grab a lock on the printer, and is waiting for the printer. At some later point, you'll switch back to A. It has all the locks it needs, it's going to proceed, and then it's going to release those locks, and then B can make progress. Okay, so what this is saying is there is a very simple and elegant way by which you can write deadlock-free code. Okay? And all that says, or all that is implying, is that you decide all the locks you need and you number them. Okay? So let's say you have a printer, your disk, your some resource R3, R4, you just number saying 1, 2, 3. Okay? Conceptually, when you design your code, you number them and say, if you need to grab multiple locks at once, you always acquire them in ascending order. Okay? Doesn't mean you need to acquire them all, but if you need this one and this one, you always grab the printer before you grab the resource R3. You never do it the other way. If you do this, then you will ensure that there is no circular weight. Okay, now you can think about a very simple intuitive explanation of how you have eliminated circular weight by simply acquiring locks in the same order. Okay, you order your resources and you grab locks in increasing order always. How does this prevent cycles? Yes.
the first thread would acquire the first lock, and then some other thread tries to acquire it.
Yes, what did you say? First thread acquires
T1
lock.
will acquire lock to printer.
Okay.
And because we're always acquiring the locks in ascending order, when T2 tries to get a lock to printer, it gets blocked. It
Yes.
cannot run.
That's true. But I'm just saying that argue why that doesn't ever lead to a cycle. You will block, but how does this guarantee you that no cycles will exist? That was it. Yes.
Any other thread that needs something with a lower priority than printer can acquire it before thread 1 acquires it, but it'll guarantee that thread 1 will be waiting on that before it releases the printer. So
Okay.
it will be waiting for thread 1, it's waiting for this, so it releases before anything else.
So I will sort of enhance your argument a little bit. So you can do proof by contradiction. Let's say that you acquired the locks in order, okay? And let's assume that a deadlock has occurred, okay? Despite acquiring the locks in order. Because a deadlock has occurred, that implies that there is a circular way. There is a cycle in the graph. That's a necessary condition. So construct some random cycle. It doesn't matter what the cycle is. Let's take this cycle. Okay. So now if you acquired the resources in increasing order, so if you just look at them, if you have ordered them in this fashion, 1, 2, 3, what does this show you? It shows you a contradiction where T4, or rather T2, okay, acquired a lock on R1, and or rather T2 acquired a lock on R3 and is requesting a lock on R1 here, okay, because it already holds R3 and is requesting R1. So it violated our ordering. This should never have occurred. If it wanted R1 and R3, it should have always requested R1 first and then R3. But in the code, if you have a cycle, because where you cycle back at the very end, you have a scenario where you're holding a lock on a higher numbered resource and still requesting a lock on a lower number resource. That's the only way the cycle will complete. Okay. That's what is shown here. You have, so if T2 wants these two locks, it asks for this one first. It already holds it, and then it's still requesting R1. So it did not, so that's a contradiction. Okay. That means your code did not actually request the locks in order. If you did that, you would have never even gotten to R3. You would have blocked on R1 first if that lock was not available. Okay. Is that clear? Okay, so you can do the same thing here. You can actually construct some sort of a. Okay, so if you construct the same cycle, you will actually hold R3 and you are requesting a lock on R1. That's the only way the cycle will finish, because you have to go back to finish the cycle to a lower number resource while holding a lock on a higher number resource. Okay, that's immediately a contradiction. So what that says is there is no way, if you actually acquire the lock in increasing order for a deadlock to occur. Okay, the simple way to write deadlock free code when you have to deal with multiple locks is always have a conceptual design or ordering in your design saying that's the order in which you acquire them. It doesn't mean you have to acquire them all. It just means if you acquire more than one, you simply always start with the lowest number and then go to a higher number and a higher number, and so on. And then that is going to break your deadlock. Okay, this is not just what you do in operating systems. This is how you write code, correct code even in Java. Yes.
It seems like that might be hard to do in general if you have like arbitrary function calls and stuff. You're not acquiring lots at once.
Yes. So I'm not saying that the code is going to get simplified, but if you can prove that in your code, that's how you acquire locks, you are guaranteed that the code will never have deadlocks. Okay. You can use tools to find that out. There are deadlock detectors that actually analyze your code, and internally they say, here are all the lock declarations. It will find some ordering and say, is your code respecting it? You can even have those kinds of tools helping you. Say, here's a potential deadlock because you did not follow this. Or you have to have some sort of an ordering, despite calling methods and functions, you have to somehow respect it. Okay. Code doesn't get simplified. All this is the correct way to write it. Your code might still be complex, but so long as this rule is followed in your code, you will not have deadlock. Okay, remember that the system is not enforcing it. Java is not going to prevent you from grabbing locks in whatever order you want. This is how you, the programmer, write correct code. The system won't prevent you from writing bad code and having deadlocks. But if you want to avoid it, that's the way to do it. Okay, so this is really the only practical way. Okay, databases do this internally. When you write transactions that require locks on tables and records, they will actually do this in order to prevent deadlocks. Okay. You can also write code to do this. Okay. The first three are not really practical ways of preventing deadlock. They enforce some restrictions that make the system somewhat unusable for most practical purposes. The last way is the only way to go. Okay? All right, so we'll go through a couple of techniques, then I'll basically switch to exam one review. So how do you do this? I think there are several different, so now here is an algorithm that you can actually use in the system to prevent locks or prevent deadlocks. So all that is actually going to do is it is going to take lock acquire requests and say that if you grant that request, will you actually see a cycle in the resource allocation graph? If so, you will explicitly deny it, okay, even though the lock may be available. Yeah, so here is here's how the technique works. So let's assume that you have a resource allocation graph that the system is maintaining. Okay. whenever a lock or a semaphore acquire or semaphore wait request comes in, you see if that lock or semaphore is available and you grant that request. And let us assume this is the current state of your resource allocation graph. Now T2 tries to acquire a lock on the printer. Okay. You say if I let that statement continue, okay, will that actually result in a cycle in the graph? And it does. So you basically say I'm not even going to let the lock acquire go through, I'm going to essentially return an error. Saying that you cannot grab a lock because that's going to result in a deadlock. Okay, what? So that's the abstract explanation of how you are going to prevent cycles in the graph. You explicitly check whether adding an edge to the graph will result in a cycle. If so, you deny. Okay. This is somewhat changing somewhat the semantics of lock acquire, because your definition of lock acquire is if you acquire, you block if the resource is not available. Okay. Here you're told that you cannot even block because blocking will cause trigger an edge that may result in a cycle, and that is going to potentially cause a deadlock. Okay. That is what this algorithm attempts to do, okay, from a system standpoint. So we have basically two definitions of the graph. A graph is said to be in a safe state if there is a sequence in which all the threads can finish without having them in a deadlock. An unsafe state is one in which some threads may not be able to make progress. Okay? And the best way to actually show how this works is through an example. Okay? Here you have multi-instance resources. Okay? And the examples are there are 3 tape drives, okay? And they are running there are programs running backups. Okay? So T1, T2, T3 are threads, not tape drives rather. They are threads asking for locks on tape drives to run backups. Okay? And we assume that T1 can ask for a maximum of 4 locks on different tape drives. T2 can ask for up to 8 locks and T3 can ask for 12 locks. Okay? It needs locks on 12 tape drives in order to finish its job. This column is showing what locks are currently being granted to these threads. Okay, 3 of those 4 locks are held by T1, 4 of those 8 are held by T2, and 4 of the 12 are held by T3. Okay? And this column that is labeled could want is simply the difference between the two. It says that T1 can ask for 1 more lock, T2 can ask for 4 more locks. That's the difference between the two, because each can ask up to its maximum and T3 can ask for 8. Okay? That is the current state of the system. Okay? And you are asked the question saying, if this is what the current system state is this a safe state or an unsafe state? Okay, a safe state is one in which all the threads can ask for their maximum and yet finish. An unsafe state is one which if all the threads ask for their maximum, there is no way to make progress. Okay? So if you are in this state, and then the worst possible scenario is T1, T2, T3 all say they want their maximum number of locks that they said they would request, which is T1 asks for 1 more lock, T2 asks for 4 more, and T3 asks for 8 more locks. Okay? Question is that safe or not? Okay, so we will assume, so one thing I forgot to mention is there are 12 tape drives in the system, okay, and of which 11 are in use. Okay. And the argument is this is going to be a safe state because if you have this worst case requirement, you still have 1 tape drive free. So there are 11 in use and there are 12, so 1 is free. So that free drive can be given to T1 because it can ask for 1 more. So now it has maxed out its requirements. Okay, so it has all the resources it needs to make progress. It cannot ask for any more. So it is going to run to completion without asking for any more locks. Okay. Once it runs to completion, it's going to release all 4 of its tape drives that it held. Okay. Those 4 could then be granted to T2 because it has asked for 4 more. That's the worst case it could ask. Then T2 has actually gotten its max. It cannot ask for any more. It will run to completion, release all of its tape drives, which was 8 that it held, and those 8 could be given to T3, which will also run to completion. So we just constructed a sequence in which each thread can ask for its maximum number of resources it said it could ask for, and yet the threads are able to finish in some order. Okay. So this is referred to as a safe state. Okay, let me show you an example of an unsafe state. Okay, now let's ask the scenario or look at the scenario at T3. So this is the current system state. Now T3 asks for one more tape, right? And that's the last one that's available. So the question is, if you grant that request, because that resource is still available, if you try to grab a lock on it, technically you should allow it because that resource is free. Okay, so if it asks for one more, does it put you in a safe state or an unsafe state? Okay, so you can analyze. Let's say you grant that request, that last tape drive is given to T3. Okay. Now the new system state is going to look like this. The first two are unchanged. Here you basically went from 4 to 5. Okay. And now there are no tape drives left, because all 12 are in use. And that's 5 plus 4 plus 3. All the tape drives are in use. Now if all the threads come back and says you need more, okay, the same worst case scenario where T1 says I need one more, T2 says I need 4 more, and T3 says I need 7 more. You will be deadlocked because there are no resources to grant. They'll all sit and wait for their allocation. There is no way to let them finish. Is that clear? So if you let that request from T3 actually be granted, you go into this unsafe state. Okay, here you are in a safe state. If T3 asks for that last tape drive, you shouldn't let it take it, because then you go into this state where there is no way if any other thread comes along and asks for more resources to let any of them finish, because everything is in use. Okay, so this we will define as an unsafe state. So what this is saying is, even if some resources are free, if you let the acquire request grab those resources, you may put the system into an unsafe state, and that could lead to a potential deadlock in the future. Okay? And so you will prevent that from happening by not granting resources that are free, because it leads to a potential deadlock. Yes, question.
So the last tape drive would never get acquired by any threads?
Okay, question. That's a good point. Good observation, actually. So the question is, can the last tape drive not be given to any thread? Okay, so T2 could ask for that tape drive, and you will again go into an unsafe state. The only way you will still stay in a safe state is if T1 asks for that tape drive. Because if T1 asks for that tape drive, you could actually give that tape drive to T1. Okay? And even now, if T2 and T3 ask for more than that, there is still a way to finish, because T1 cannot ask for anything more. It got its last tape drive that it wanted. It will finish to completion at this point without blocking or waiting for any more resource. At that point, it will release those 4 tape drives it holds, and then you can finish T2 and T3 in that order. Okay? So the only way you can actually allow any thread to actually acquire the last tape drive is to let T1 get it. Yeah, other two, if they actually ask for that last one, you put the system in an unsafe. Okay? Yes.
This assumes that you cannot take back a lock.
Yes. So this is assuming that once you grant a lock, you cannot take back a lock. But it is making a subtle change to acquiring of a lock. We always said you acquire a lock, if the lock is available, you take it. Here the lock on that last tape drive is available, but you don't let whoever comes along first to take it. Okay? You say that doing that may put the system at harm or at risk, so we will not allow those tape drives. So you will actually make them block in this case. Okay? Changing the semantics of a lock somewhat to prevent deadlocks from occurring. Okay, is that clear? Right. So that is safe and unsafe state. You could do the same thing. So this computation that I just showed you, you could simply do this analysis using a request allocation graph. Basically what happens in that case is you are going to essentially see that granting that resource will result in a deadlock. Okay? And as a result of which you will refuse to grant that resource even though it is free. Okay? Now how to do all this, and there's this algorithm called the banker's algorithm to implement this idea. We will come back to next time, because I have only 20 minutes or 15 minutes left. I'm going to spend the remainder of the time actually looking at the exam review, or giving you some notion of what to prepare for the exam. Okay. So as I mentioned at the very beginning of the class, I put up a solution to the sample exam on Moodle. So if you looked at the sample exam, you should go to Moodle and look at the solutions to make sure you understood the material. So I'll first start with how you should prepare for the exam. Okay. Also, this is the course web page. All of this material is also on the Moodle site. Okay. First 8 lectures only. You don't need to worry about lecture 9 or today's lecture for exam 1. That's for exam 2. So my suggestion for sort of doing a smart sort of a review of the material is to start with the course slides, not start reading the book from page 1 to whatever, chapter 6. Okay? Because there's a lot of material in the book that we haven't covered in class. I do not expect that you will know that material and you will not be tested on the material. The only material that we are going to be tested on is what we have covered in class. Okay. So the right way to start reviewing the material is to start with the slides. Okay. Anything that's on the slides, fair game for the test. Something that's not on the slide but is on the book, you can safely assume that you are not going to actually be asked questions about it. Okay. So start with the slides. Okay. There are notes that we have put up for that transcribe what I say. Okay, so you can review the slides, review the notes, make sure you thoroughly understand it. Okay, once you have reviewed the class slides, then you go read the book that has material corresponding to what's on the class slides. There are other things in each chapter that we haven't covered that you can ignore. Okay, that's the right way to study. The course videos are also there. If you missed a lecture or you forgot something, you can go review it. That's going to be somewhat cumbersome because each video is 1 hour, 15 minutes. But it is there if you need to go review some material. Okay. So the smart way to study for the test is to start from the slides and make sure you thoroughly understand everything we have done on all of the lecture slides. If you understand that, I think that you will not have problems with whatever we are asking on the exam. Because the questions on the exam directly go back to material we have covered in class, and they should be on the slides in some shape or form. Okay. So with that, let me go back and now start reviewing some of the material. So this is 8 lectures worth of material. Okay. So first 3 lectures that we did were mostly introductory materials. Okay. Still going to be tested on it. Okay. The very first one was just a history lesson, if you remember. The next 2 lectures basically said computer architecture, hardware concepts, as well as OS architecture, OS concepts at a very high level. So these are all things you should sort of know from those lectures. Okay, we talked about Moore's law, okay, what it is, how it has impacted technology in terms of OS evolution from old mainframe days to what you see today. Okay, that was sort of the history lesson we did in lecture 1. Okay. In lecture 2, we said we did a review of computer architecture. We showed what are the key concepts on how that you see on a CPU. We looked at why some of those features are there and how they help us. Okay. Everything from traps, interrupt vectors, protection bit, base limit registers. We went to very specific features. Okay, and we said, how does it make the life of an operating system easier in terms of functionality it wants to implement. Okay. So go review that material. Okay. Understand what are those hardware features, what do they do, okay. And how does it help the OS. Okay. That's really the part of computer architecture you need to know here. You don't need to know other extraneous details that we did not cover. Only parts that sort of have an implication on OS design. Okay. Third lecture, we looked at OS architecture. Okay. We talked about various architectures for designing an OS kernel, monolithic kernels, where everything is one large blob of code, layered design where you have layers that talk to the layer above and below. Okay. Microkernel architecture where the kernel is actually very small. Most of the functions are written as user processes in user space. Okay. And the modular architecture where you basically have a core kernel but you extend its functions by loading modules at runtime. So everything still runs in one sort of single address space, but the code is written in a modular way. It tries to combine the best features of microkernel and efficiency of the monolithic architecture and so on. Okay. So what are these architectures? What are their benefits, limitations? That's what you need to understand. Okay. We also spent these first 3 lectures talking a fair bit about system calls. Okay, they are the interface that the kernel exposes. We said, how do you implement a system call that it causes a trap? You go into the kernel goes and sort of executes the code for the system call and returns back to the user process. Okay, all the steps that need to be performed to implement system calls. Okay, that's first 3 lectures of introductory material. I'll pause for a question or two if there are any. Okay. Next major topic was processes and then came threads, of course. So all the stuff you need to understand is what is a process. Okay. So basically the address space, what does it contain, multiple segments, etc. Okay. We defined this notion of a process control block. That's the key data structure that the OS kernel maintains to track processes. Okay. So what is contained in it, all the state of the process, all of that stuff you need to know. Okay. We talked about the execution state of the process. Okay. There's this transition diagram we showed where we said there could be one process could be in one of several states: new, ready, running, wait, terminated. Okay. So you need to know what those states are when you make transitions from one to another. Okay. We said how does the OS kernel keep track of processes? For every state there is a queue. If you are in a particular state, your process control block entry is in that queue. So if you are in the ready state, you are in the ready queue. Okay, if you are in the wait state, you are in the wait queue. Okay, if you are in the running state, you are in the run queue. Okay. We defined this notion of a context switch. That's basically the set of operations that must be performed to switch from one process to another. Okay, it's all bookkeeping work. You save the state of that outgoing process in the process control block. Okay, you will then run the CPU scheduler that will pick the next process to run. You will look at its process control block and reload its state into the registers, okay, and other hardware structures. And then you can start executing the data process. That's a context switch, all the operations you need to perform. Then we defined a thread and said how does a thread how is it different from a process? By process, essentially we mean a single threaded process. That's a more formal definition of a process. A thread is basically a execution control flow to an address space. Okay, what we are calling process can have multiple threads that run through. They all share the address space. Each thread gets its own stack. Okay? They share the heap. They share the code segment. Okay? Each thread gets its own program counter and its own stack. Okay? And threads allow you to implement concurrency through that address space. Okay. We spent quite a bit of time talking about user level threads and kernel level threads. Okay. Kernel level threads are threads the kernel is aware of. User level threads are implemented by user library without requiring kernel support. Okay. You should understand that the pros and cons. Okay. When the kernel knows about threads, it can take into account the presence of threads. When you do scheduling, you get better concurrency in multi-core systems and whatnot. User level threads, you are not bound by whatever the CPU scheduler is doing. You can implement a thread scheduler in user space that is most suited for your program. You can pick whichever threading library you want that gives you the best performance, for instance. And it is more efficient because switching between threads is a function call to a library. In kernel level threads, context switching between threads involves actually OS. It's basically something that the OS has to do. Okay. So efficiency considerations, advantages, disadvantages, all of these things you need to do. Okay. The last point in processes and threads was some system calls for process management. We talked about 4 exec wait. You need to know what they are. A 4 creates a copy of the parent process. Exec allows a process to start executing a new program. Okay, wait allows the process to wait for another process to terminate. Okay, so these are the 3 key system calls for process management. Okay, you need to understand how they work, okay, and write some simple pseudocode or analyze some simple pseudocode that has 4 in exec and explain what it does or show how to implement a certain process tree. Write code where A forks B, B forks C, for instance. Something like that. Are there any questions on this? Yes.
Where can you know the variation of the execute method? The other execute the
Yeah. So there are many variants of exec. There are many variants of wait. You don't have to write real code. Any code that you have to write is a pseudocode. So you can simply say wait and what variant it is, you can pretty much ignore. Because it's more important what it is doing rather than the variant and exactly how many arguments you pass. That's not really important. We're testing you on concept, not on whether you write code. That part you do in the lab. Okay? Yes.
Do we need to study the algorithm for process scheduling?
Yes, I haven't come to that. That's the next slide. Okay, this is just processes and threads. Okay, so everything lecture 1 through 8. Okay, that includes scheduling as well. So CPU scheduling was the next major lecture we had. Okay, so here we looked at several algorithms. First come, first serve, round robin, shortest job first, multi-level queue, lottery first scheduling. Okay, 5 different policies. Go and understand each of them. Okay. You should be able to, given some policies and some jobs that come in, be able to say when does each job finish when you use a particular policy. We did several of those exercises in class. Okay, same kind of stuff you should be able to do. You need to know what is preemptive, what is non-preemptive. Non-preemptive scheduler, once you schedule a job or a process, lets it run to completion or until it does IO and gives up the CPU. Preemptive schedulers have the notion of a time slice. You get, see, once you run on the CPU, you can run until the end of your time slice before you give it up. Okay. How to choose a time slice, we said if you make it very large, you have more efficiency if your context switches, but wait times increase. You make it very small, it's more fair, but then you have more context switches happening because you're switching quickly between from one process to another. So you need to balance those trade-offs. Okay, so that's how you choose a time slice. And in particular, when we talked about multi-level feedback queue, we talked about this notion of a IO bound process, CPU bound process, and said we like to give priority to IO bound processes because they are the short jobs. You let them run quickly and then you focus on your longer CPU bound jobs. Okay, so why do we treat them this way? In order to reduce wait times for IO bound jobs. How do you do that? You use multi-level feedback queue, you use shortest job first. These are schedulers that explicitly favor shorter jobs or IO bound jobs. Okay, so all of the stuff that we talked about in that class, you need to remember. Okay, so things you should be able to do. I already said, given a list of processes, arrival times, etc., you should be able to figure out completion time and wait times. Okay, and maybe you probably saw the sample exam where we had a small variant of some scheduling policy, and you are asked to explain how it behaves, for instance. Questions here? Okay, so I'll go through the last one very quickly. Okay, so last topic was synchronization. Okay, we had 2 or so lectures on this. So we learned about 3 different primitives. Okay, locks, semaphores, monitors. Okay, you pretty much need to know what they all are. Okay, so what is mutual exclusion? Okay, definition of it. What's a critical section? Okay, what are locks and semaphores? Okay, semaphores we said are generalization of locks. They allow you to do 3 different things. Okay, you can have binary semaphore, which is a lock, counting semaphore, which is a lock that protects multiple resources, and you can use semaphores to implement scheduling constraints. You can decide how threads run, for instance. Okay. So that's basically semaphores. Monitors are higher level constructs where the language has built in some support that makes writing code with synchronization easier. Okay, you don't explicitly need to grab and release locks. This monitor will do it for you in Java, at least, where there's built-in support for that. And then we mentioned this notion of a condition variable, which allows you to go to sleep inside a lock atomically and give up the lock when you are waiting for a certain condition. And in that context, we showed how to implement locks and semaphores using enabling and disabling interrupts and using test and set instructions. Okay. Go and understand how hardware features like interrupts and test and set allow you to implement synchronization. Okay. In that context, we also talked about busy waiting when we did test and set, and we said busy waiting wastes CPU cycles. We should try to avoid it, and we saw implementations that reduced it or eliminated it. Okay. So that basically is the implementation of those primitives. We looked at interrupts and test and set. Okay, those are the 2. So do go look at those as well. Okay, things that you should be able to do, basically, if you are given some code with lock semaphores, reason about it, or you may be given a short problem saying write some code with locks, monitor, semaphores that implement some simple synchronization. Okay? Again, whenever you are asked to write code, keep in mind we are only looking for pseudocode that has design level correctness. Okay, we are not expecting that you will write syntactically correct code that's going to start running when you, yes, run it.
Deadlocks are on test.
I'm sorry, what? No, actually that's typo. There is no deadlock. It's only starvation. Okay. The deadlock part we can avoid. I mean, that was covered in dining philosophers, but dining philosophers are removed from the deadlock material is not there, but even in dining philosophers we had mentioned it, so we can ignore it. Okay, so that's basically all I have as far as the review is concerned. Yeah, so again, the only main takeaway point is don't start reading the book from first chapter to sixth chapter. That is going to waste a lot of your time. The exam is tomorrow. So if you're still not finished your review, the best way is to start with the course slides. And then review whatever material you need to review in the book or the notes or whatever. Yes, last question.
I don't think the quiz is posted on the website. The solutions to the quiz.
The discussion, okay, I should go look at what is the status of it. The homeworks and other things have been returned. I think the hard copy of the homework I did not hand out yet. So what we did is we went back into Moodle and posted any comments on where you may have lost points on. So if you did not get a full score and you need to know where you may have some points taken off, go look at the full feedback for your homework. Okay? Sample solutions are also on the Moodle site.
Are these slides going to be online soon?
So I will put them up right now.
Are you studying today? Yeah. I was going to be aware of this 12:30 to 4, and I'm hoping to be there later too. So. Okay. That's